Let's talk about something you use every day, but rarely notice: mechanisms. Think about your car's suspension. As you drive over a bump, metal bars and joints move in a controlled way to absorb shock and keep your ride smooth. This precise movement is the secret behind everything from engines to robots. Pop the hood of a car. Inside, pistons move back and forth thanks to the slider crank mechanism, converting spinning motion into linear motion. Each part is designed to move in a specific way. No wobbling, no chaos. Robotic arms in factories are another example. Each joint adds a degree of freedom, allowing for pinpoint accuracy. Even your body is a masterclass. Your elbow hinges, your shoulder rotates and swings. Different joints, different freedoms. Engineers mimic this, designing everything from prosthetic limbs to desk lamps by controlling movement. It's all about limiting and guiding motion for precision and reliability. That's the elegant math behind how things move. So, what's a degree of freedom, or DOF? It's simply the number of independent ways an object can move. Imagine a video game character: forward, back, left, right, up, down, 3 ways to move. On a flat surface, a triangle can slide left, right, up, down, and rotate. 3 DOF. In 3D, an object can move in 6 ways, 3 translations and 3 rotations. But in machines, we rarely want all that freedom. Too much movement is chaos. Joints are used to remove unwanted freedoms. A hinge, for example, only allows rotation, not sliding. By connecting parts with different joints, we constrain motion to exactly what we want. Engineering is about controlling freedom, giving just enough movement for the job. That's how we get everything from stable bridges to precise robots. Every mechanism starts with potential movement, and we use joints to shape it. The art is in knowing what to allow and what to block. That's the foundation of machine design. How do we count degrees of freedom? Start with the basics. In 2D, each link starts with 3 DOF. In 3D, it's 6. One link is always the ground. It doesn't move, so 0 DOF. When you connect 2 links with a joint, the joint removes freedoms. A pin joint, like a hinge, allows 1 rotation, so it removes 2 freedoms in 2D. A slider allows 1 translation, also 1 DOF. More complex joints, like a pin in a slot, allow 2 DOF. The more a joint allows, the less it removes. The process: start with total possible freedom. Subtract the constraints from each joint. Each joint's type determines how much it constrains. It's just accounting. Add up freedoms, subtract constraints. That's the logic behind all those formulas. Engineers love shortcuts, so here's the one you'll use most: the Kutzbach criterion. For planar 2D mechanisms, the formula is m equals 3n1. 2j. M is the final degrees of freedom. N is the total number of links including the ground. J is the number of simple 1 DOF joints, pins or sliders. Each link, except the ground, starts with 3 DOF. Each joint removes 2. Step 1. Count links. N. Step 2. Count joints. J. Plug into the formula. If m equal 1, you have a mechanism with 1 input. M equals 0 means a rigid structure. M or 1 means multiple inputs needed. M0 means it's over-constrained. This formula is your cheat code for most linkage problems. Let's build a classic, the 4-bar linkage. It's everywhere. Windshield wipers, construction equipment, kinetic sculptures, 4 bars connected in a loop. 1 is fixed, the ground. Step 1. Count links. Ground plus 3 moving bars equals n equals 4. Step 2. Count joints. 4 pin joints connect the bars, j equals 4. Plug into Kutzbach. M equals 3, 4 to 1, 2, 4. X 9, 8 equals 1. 1 degree of freedom. Control 1 link and the whole system moves predictably. That's why it's so useful. One input, one output, reliable motion. This is the hello world of mechanisms. Always count the ground as a link. 4 links, 4 joints, 1 predictable movement. That's the power of the 4-bar. It's simple, elegant, and everywhere. Now you know why. Next up, the slider crank mechanism, the heart of every piston engine. It converts spinning motion into linear motion, powering cars, pumps, and more. Let's count ground, engine block, crank, connecting rod, piston, N-4, joints, 3 pins, rotations, and 1 slider, translation. J-4, plug into Kutzbach, M-3, 4 to 1, 2, 4, is 9, 8 is 1. 1 degree of freedom. Turn the crank, and the piston's motion is fully determined. That's why engines work. 1 input, 1 output, total control. The slider crank is just a 4-bar with a sliding joint. Same math, same result. This principle powers everything from cars to compressors. 1 input, 1 predictable result. That's the beauty of mechanism design. Simple math, powerful machines. Now you see the connection. Let's look at an open chain, a simple 2-joint robot arm. Imagine a base, an upper arm and a forearm. N=3. 2 revolute joints, shoulder and elbow. J=2. Kutzbach. M=3, 3, 1. 2, 2, 6, 4, 2. 2 degrees of freedom, 1 for each joint. To place the robot's hand anywhere, you need to control both joints. That's why robot arms have multiple motors, 1 per DO-off. Open chains are common in robotics and automation. The math is the same. Count links, count joints, plug in. More joints, more freedom, more control, more complexity. This is the foundation of robot kinematics. Simple math, powerful movement. That's how robots reach and grab. What if M is 0? That means no movement, a rigid structure. Example, a triangle made of 3 bars and 3 pin joints. N=3, J=3, Kutzbach. M=3, 3 to 1, 2, 3, 6, 6=0. It's locked, perfect for bridges and trusses. If M0, it's overconstrained, too many links or joints. This can cause internal stresses and problems in real structures. Sometimes the formula can be fooled by special geometry. For example, a 5-bar pentagon may seem to have M=2, but it's unstable. Some mechanisms work even when the formula says they shouldn't. So use the formula as a guide, but always check with real-world testing. The math is a starting point, not the whole story. Always confirm with physical models or simulations. Why does all this matter? Because degrees of freedom are the foundation of machine design. If you don't know the DOF, you can't control your machine. In robotics, every joint needs a motor, 1 per DOF. The math tells you how many controls you need for precise movement. It's not just for robots. Car steering, airplane landing gear, even pop-up books rely on this. DOF analysis ensures safety, predictability, and creativity in design. It's the first step in turning ideas into working machines. Mastering this lets you invent, innovate, and solve real problems. The simple math of motion is the key to engineering magic. That's why degrees of freedom matter. Everywhere, every day.